Welcome to our presentation on bioclimatic design, focusing on site-specific strategies. I'm Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. In this video, we will discuss how building site conditions and natural environments influence sustainable architecture design. Reference books include Victor Allguy's Design with Climate and Barber's Modern Architecture and Climate Design Before Air Conditioning. We discussed the net zero design approach in the zero design videos. The net zero energy approach on the left consists of bioclimatic design, energy efficient systems, and renewable energy integration. The design goal is to reduce energy use through bioclimatic strategies and energy efficient building service systems. This video focuses on bioclimatic design. Then, the on-site renewable energy system is integrated to support building operations. The net zero carbon approach on the right requires additional strategies beyond the net zero energy approach. Additional strategies include the use of renewable, bio-based construction materials and the integration of vegetative systems, both of which offset carbon emissions from the building overall. The final performance goal is to design buildings that achieve both net zero energy and net zero carbon. For more information, refer to the additional videos indicated in the slide. In summary, bioclimatic design is a fundamental step toward net zero building design strategies that utilize climate and site resources to create a healthy, energy-efficient built environment. Bioclimatic design enhances occupant comfort, health, and well-being through natural ventilation, shading, daylighting, and moisture control. Bioclimatic design minimizes the use of active building systems and reduces energy consumption in heating, cooling, ventilation, and lighting energy. Bioclimatic design preserves natural resources while protecting surrounding ecosystems, such as bodies of water, vegetation, and natural habitats. Key site factors affecting building performance and occupant comfort include vegetation, topography, water features, and natural habitats. For example, vegetative landscapes create moderate microclimates through shadow, evapotranspiration, and wind breaks. Hills block cold winter winds and help divert water flooding. Ponds and water features, along with vegetation, not only cool the environment but also control rainwater runoff. Natural habitat in the built environment supports biodiversity and ecosystems. Vegetative sites create localized microclimates with distinct temperature, light, and moisture conditions. Even within a small area, sunlight and shade patterns shaped by surrounding buildings and landscapes influence thermal comfort and efficiency. This slide illustrates that the mean radiant temperature, MRT, of a skylight is as high as 39 degrees Celsius MRT, whereas the tree measures 23 degrees Celsius MRT. Bioclimatic design starts with understanding the site's microclimates and placing each zone in its optimal local environment. Vegetative systems are a powerful tool for microclimate control. This slide illustrates a comparison between a vegetated green roof and a conventional bare roof. The data is striking. The surface temperature of a traditional roof reached up to 151 degrees Fahrenheit, whereas the green roof stays around 74 degrees Fahrenheit. These large temperature differences occur because plants and soil provide shade and dissipate heat. Incorporating green roofs as a bioclimatic strategy not only reduces temperature, but also helps mitigate heat island effect and surface water runoff. The figure in this slide highlights the multiple cooling mechanisms of a tree. Leaves intercept and reflect solar radiation, preventing the ground from heating up. They provide shade and cooling for people and the ground beneath. The water in the soil and leaves further cool down the environment through evaporation and transpiration respectively. Planting trees around buildings and open spaces can reduce peak summer temperatures naturally. These vegetative strategies improve outdoor comfort, lower cooling needs for nearby buildings, and even benefit air quality. By strategically placing and preserving trees, We create a microclimate where nature itself provides much of the cooling. Another bioclimatic strategy is on-site rainwater management using vegetated features. This slide shows a typical design of a bioretention along a city street designed to naturally manage stormwater runoff. The diagrams on the top right illustrate a cross-section of the Bioswales layered construction and conceptual stages labeled capture, store, and infiltrate. The concept drawings below show a street-side bioswale with curb notches that direct road runoff into a planted basin. Each component in the system plays a specific role in filtering and controlling rainwater. Refer to the flooding resilient design videos for more details about this specific flooding prevention strategy. This figure on this slide shows how an ordinary city street was retrofitted into a lush, water-managing landscape. The design features a continuous stormwater spine, a series of linked bioswale planters running along the street, which capture and treat runoff from a large impervious roadway and sidewalk. In terms of capacity, once fully implemented, this green street can manage millions of gallons of stormwater each year that would otherwise flow into sewers. The project demonstrates a holistic approach. It creates a safer, more attractive streetscape with trees and plantings, while performing serious environmental engineering work under the surface. By mimicking natural drainage in the urban context, such designs exemplify rainwater runoff control as an important flood-resilient strategy in bioclimatic site design. Bioclimatic site design enhances the living ecosystems of a site through habitat preservation and biodiversity. Biodiversity on site contributes to ecological resilience and climate adaptability. We covered biodiversity measures in the Sustainable Facade video. Ecologists measure biodiversity at multiple scales using alpha, beta, and gamma diversity. Alpha diversity refers to the number of species in a specific urban area, which is essentially the species richness at one site. Beta diversity compares differences of unique species in one site in relation to other sites. Gamma diversity is the overall species diversity in a region, encompassing all the sites together. Let's look at a famous example of habitat integration in the ACROS Fukuoka Prefectural International Hall in Japan. This building is essentially a stepped urban park, a true bioclimatic design landmark. ACROS Fukuoka was built on what was the last major open space in downtown Fukuoka. The architect's solution was to give back a green mountain of terraces on the building. The south facade is a series of 15 lush garden terraces ascending the full height, seamlessly extending a neighboring park up the structure. The result is an enormous increase in urban greenery and habitat right in the city center. Besides boosting biodiversity, ACROS has a significant microclimate impact. A thermal survey by researchers demonstrated that its green terraces and rooftop garden noticeably alleviate the urban heat island in that area. The vegetation cools the building and its surroundings, much like a natural hillside. Importantly, ACROS achieves all this while providing human benefits too. It doubled the public park space where the terraces are accessible to people. Inside, the building's energy use is reduced thanks to the natural insulation and cooling from the planted facade. This case illustrates how ambitious bioclimatic site design can create a symbiosis between architecture, site, and nature. The building becomes a living part of the local ecosystem, improving the city's climate, offering citizens health, and providing habitat in the sky. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future.